Welcome to Scoli Sleep Stories. Before we begin, take a moment to get comfortable. Let the day soften around you, and settle in for a calm documentary made for curious minds. If these stories help you rest, learn, or simply enjoy a quieter part of the day, please consider liking this episode and subscribing to the channel. Now, when you are ready, let us begin. Chapter 1. Before the Compass. Reading the Living World. At the edge of an old settlement, a narrow path passes between open fields and enters a grove of trees. The earth along its center is firm and smooth, darkened by generations of footsteps. Some travelers followed it carrying baskets or bundles. Others led animals, walked beside friends, or returned quietly at the end of a long day. No sign marks the way, yet the path itself is a kind of record. It bends around a broad-rooted tree, descends toward a stream, and rises again beside a pale stone warmed by the afternoon sun. Someone who knows this path does not need to ask where it leads. The shape of the ground is familiar. The sound of water announces the stream before it comes into view. A gap between the trees reveals the next hill. Each detail belongs to a sequence held in memory. This is where the story of navigation begins. Not with an instrument, but with attention. Navigation is older than writing, and far older than the magnetic compass. Long before directions could be drawn on paper, people traveled between camps, villages, hunting grounds, grazing lands, gardens, markets, and harbors. They crossed valleys and followed rivers. They moved along coastlines, passed through mountain gaps, and ventured onto open water. To make these journeys, they practiced what we may call wayfinding. Wayfinding means using observation, memory, experience, and learned practices to travel from one place to another. A traveler on land might keep a ridge on the left and a river on the right. A valley could offer a natural passage between high slopes. A mountain pass might be recognized by the shapes of two peaks, one rounded and one sharp, a prominent rock, an unusually tall tree, or a headland reaching into the sea could serve as a landmark. A landmark is simply a visible feature that helps someone recognize a place or follow a route. Yet a journey was rarely remembered by one landmark alone. More often it unfolded as a chain of familiar moments. Follow the stream until it divides. Take the branch that flows from the west. Continue until the ground becomes stony. Rest beside the spring below the leaning tree. Cross the river at the shallow ford. Beyond the crossing, find a narrow trail rising through the grass. Such knowledge can be as orderly as written instructions, even when no words are placed on a page. Routes have long been preserved through oral teaching, place names, songs, stories, demonstrations, and repeated journeys. An experienced traveler might guide a younger person along the same course many times, pointing out not only what to notice, but how each feature changes with the season. A ford that is gentle in summer may become deep after rain. A spring may be hidden by new growth. A pale cliff may glow in morning light, then blend into shadow late in the day. The land is not a fixed diagram. It changes, and the traveler learns to read those changes. Place names can hold practical knowledge. A name may recall the shape of a hill, the presence of water, a plant growing nearby, or an event associated with a crossing. A story may describe a route while preserving relationships between people and places. A song may arrange landmarks in the order they appear, giving memory a rhythm that can be carried over a long distance. Oral geographic knowledge is not vague simply because it is spoken. It can be detailed, systematic, and precise. Accuracy grows through careful teaching, correction, and the experience of making a journey again and again. Along rivers and coastlines, a route may seem simple. Follow the water, and eventually it will lead somewhere. But finding a direction is not quite the same as finding a destination. A river may guide a traveler through a region, yet local knowledge identifies the safest crossing, the correct tributary, or the landing place hidden behind reeds. A coastline may help a boat remain oriented for many miles, but the boat must still find the right beach, harbor, or opening between rocks. Knowing that a village lies downstream is useful. Knowing where to leave the river is what completes the journey. Navigation has always involved these layers of understanding. There is the broad direction of travel, and there is the close knowledge of arrival. There is the distant mountain that can be seen for hours, and the small turn beside a spring that must not be missed. There are places to rest, places to cross, and places where water can be found. Weather adds another layer. In many regions, winds tend to blow more often from a particular direction during a certain season. Such a common pattern is called a prevailing wind. This does not mean the wind always behaves in the same way. It means that, over time, one direction is usual enough to become helpful. A traveler might feel a prevailing wind against one cheek while walking a familiar path. A sailor might recognize the season from the wind's direction and character. Currents could carry a vessel along a coast, while ocean swells, the long and rolling movements of water shaped by distant winds, could provide clues about direction beyond the immediate surface of the sea. The sun offered guidance as well. Its movement across the sky gave travelers a broad sense of direction. Shadows changed in length and angle as the hours passed. The moon and stars provided further patterns, especially to those who had learned their seasonal appearances. None of these signs needed to stand alone. A skilled wayfinder could compare one clue with another. The wind might agree with the waves. A familiar headland might appear where it was expected. The angle of the sun could confirm the direction already suggested by the land. Even on a known route, travelers needed some sense of how far they had gone. They might estimate distance by time, pace, effort, or the usual speed of a boat. They remembered turns and judged how each part of the journey related to the last. This kind of estimation is known as dead reckoning. It means estimating a present position from a known starting point, the direction traveled, speed, elapsed time, and changes of course. The name may sound technical, but the basic practice is familiar. If you leave a village, walk north for an hour, turn toward the hills, and continue for another hour, you form a mental picture of where you are in relation to where you began. Dead reckoning is not perfectly exact. A walker slows on steep ground. A boat drifts with wind and current. A path bends gently without seeming to turn. So the estimate must be checked against the surrounding world. A ridge should appear ahead. A river may be heard nearby. A familiar island may rise above the horizon. In this way, memory and observation work together. The traveler carries an idea of the route, then quietly compares that idea with what appears. Few examples show the richness of navigation without magnetic instruments more clearly than the traditions of the Pacific. Across the world's largest ocean, island communities developed highly skilled ways of traveling between places separated by wide reaches of water. Different Pacific peoples developed different practices, suited to their own islands, vessels, routes, seasons, and histories. These traditions should not be treated as one single method, yet many reveal the same patient habit of bringing numerous signs together. A navigator might steer by stars during the night, and by the sun during the day. Winds and wave patterns could help maintain direction when familiar islands were far below the horizon. Clouds might sometimes offer clues near land. Birds could also provide useful information, especially species that feed at sea and return to islands. But animal behavior is not an infallible natural signpost. A bird may wander, feed, rest, or move for reasons the traveler cannot know. Clouds may form without an island beneath them. Winds shift, and different swells may cross one another. Skill lies not in trusting one sign without question, but in comparing many signs continuously. Throughout the voyage, the navigator keeps a careful mental reckoning. Where did the journey begin? How long has the vessel traveled? How has its course changed? How might wind or current have carried it to one side? This continuous awareness is patient and active. The navigator notices the stars, the sun, the wind, the waves, the clouds, and the movement of birds. Each sign becomes part of a larger pattern. In modern Polynesian wayfinding, navigators may use what is called a star compass. Despite its name, it is not a handheld magnetic instrument. It is a learned mental framework. The horizon is understood as a circle, divided into named directional regions. Stars are remembered by the places where they rise and set along this horizon. A star rising in a known region can guide a course for a time. As it climbs too high to remain useful, another star may take its place. The remembered setting place of a star can preserve its direction even after the sky begins to brighten. Through the day, the sun, winds, swells, and other signs continue the pattern. The navigator does not depend on one fixed guide. Instead, guidance passes gently from one familiar sign to another. Learning such a system requires more than memorizing a list of stars. It involves long practice on the water, close instruction, repeated journeys, and an understanding of how the sky changes through the night and across the seasons. Knowledge joins with experience until the horizon itself becomes meaningful. Elsewhere, different landscapes called for different forms of attention. Travelers moving through valleys might follow rivers, slopes, and mountain passes. Along a coast, headlands, islands, currents, and landing places could shape a remembered route. In every region, methods developed according to the local landscape, waters, seasons, vessels, and cultural knowledge. There was no single universal method because there was no single universal landscape. This does not mean every journey was easy or that every sign was clear. Mist could hide a ridge. Floods could alter a riverbank. A fallen tree might obscure part of a path. At sea, wind and current could move a vessel away from its intended course. Yet uncertainty encouraged careful comparison. One clue supported another. Memory was tested against what appeared ahead. Experience taught the traveler which signs were dependable, which changed with the season, and which needed to be treated with caution. And knowledge was shared. A child walking beside an experienced traveler might be asked to notice where the valley narrows. A young sailor might learn to recognize the feel of crossing swells through the movement of a vessel. A place name might be repeated until its location and meaning settled into memory. Gradually, a route became more than a line between 2 points. It became a sequence of relationships. Hill and stream, wind and season, bird and shore, star and horizon. On the old footpath, evening now gathers beneath the trees. The pale stone is dimmer, and the stream reflects only a narrow band of light. Familiar features soften at their edges. The ridge remains, but its grasses and scattered rocks merge into one dark shape. The traveler continues toward the coast, guided by the slope of the ground and the quiet sound of water moving toward the sea. At the last rise, the trees open. A headland rests against the fading horizon, and beyond it the ocean extends into the distance. For most of the day, the land has offered one guide after another: the worn path, the turning stream, the pale stone, and the distant ridge have formed a pattern that can be remembered. But now daylight is leading the path. The guideposts on the ground are becoming harder to distinguish. The traveler pauses beside the shoreline and listens to the steady water. Then, as the coast settles into shadow, they lift their eyes. Above the darkening sea, the first stars are beginning to appear. Chapter 2: The Reliable Sky. Above the darkening water, the first stars appear one by one. Their reflections tremble with the small movements of the sea, while the stars themselves seem clear and distant. The traveler standing on the shore recognizes a few familiar patterns. As the night deepens, more of the sky becomes visible, until the headland is only a quiet shape beneath a great field of light. Long before there were compasses, people learned to read this field much as they read a riverbank or a mountain path. They watched where the sun rose, where shadows fell, and how certain stars moved through the night. This practice is called celestial navigation. It means finding direction and sometimes position by observing heavenly bodies such as the sun, moon, planets, and stars. The word celestial simply means belonging to the sky, yet celestial navigation began with observations close to everyday life. Morning light entered a doorway from one side. At midday, a tree's shadow gathered near its trunk. In the evening, the light withdrew toward the opposite horizon. Repeated over many days and many seasons, these familiar changes became a dependable source of knowledge. Night passes over the coast. Then at dawn, the edge of the sea grows pale. The sun rises, laying a quiet path of light across the water. Its daily movement provides broad information about east and west. It appears in the eastern part of the sky and crosses toward the western part because Earth is turning beneath it. A traveler can therefore use sunrise or sunset as a general guide. There is, however, a gentle complication. The sun does not rise exactly due east and set exactly due west on every day of the year. That happens only around the equinoxes, the 2 times each year when day and night are approximately equal in length. In other seasons, the points of sunrise and sunset shift along the horizon. Their apparent positions also depend on where the observer is standing upon Earth. A patient watcher comes to know these changes. Sunrise may appear near one notch in a ridge during one season, and near another notch several months later. A community may remember the place where the first light appears at a particular time of year. A sailor may recognize how the sun's path changes between summer and winter. Direction is not always taken from a single glance. Often it is gathered slowly through familiarity. As the sun rises higher, it creates another useful guide, the shadow. Imagine a straight stick placed upright on level ground. An upright object used for observing shadows is called a gnomon. The name may sound specialized, but the object itself can be very simple. It may be a post, a staff, or even a carefully chosen stone standing vertically beneath a clear sky. In the morning, its shadow stretches long across the ground. As the sun climbs, the shadow slowly shortens. It also changes direction, moving almost like the hand of a broad and silent clock. Around the middle of the sun's daily passage, the shadow reaches its shortest length. This time is called local solar noon. Solar noon is not always the same as 12 o'clock on a modern clock. It is the moment when the sun reaches its highest point in the sky for that particular place and day. The word local matters because this moment occurs at different times in places east or west of one another. By marking a shadow over time, an observer can establish a north-south line. One method is to note the direction of the shortest shadow around solar noon. Other methods compare equal shadow lengths before and after noon. With level ground, a vertical stick, enough sunlight, and careful observation, the marks can reveal a useful line of direction. The method asks for patience. The ground should be reasonably even. The gnomon should stand straight. The observer must wait while the shadow changes, sometimes for several hours. Heavy clouds may soften or erase it. Near dawn and dusk, shadows grow very long and can be difficult to judge precisely. On the moving deck of a vessel, where the observer and the upright object rise and tilt with the water, the task becomes harder still. Yet on a still patch of land, the slow shadow offers a calm demonstration of order. Nothing about it seems hurried. The sun moves across the sky, the mark advances over the earth, and direction emerges from the relationship between them. As evening returns, the shadow lengthens and fades. Then the stars resume their watch. In the northern hemisphere, one star has long been especially useful. Polaris, often called the North Star, lies close to the North Celestial Pole. A celestial pole is a point in the sky toward which Earth's rotational axis appears to point. If the sky were imagined as a vast dome turning above the landscape, the celestial pole would be near the center of that apparent turning. Through the night, many stars seem to circle this point. They rise, travel in broad arcs and set, or they wheel around without dropping below the horizon. Polaris appears almost still among them. To someone watching from a quiet northern shore, it can seem like a small peg around which the heavens slowly turn. Finding Polaris gives a good indication of north, though not with mathematical perfection. The star is close to the North Celestial Pole, but it does not rest exactly upon it. Polaris also traces a very small circle as the hours pass. For ordinary wayfinding, this difference may be slight. Still, careful navigators learn that every guide has its limits. Polaris has not always held the same place of importance. Earth's rotational axis changes direction very slowly, rather like the axis of a gently wobbling spinning top. This gradual change is called precession. It takes many thousands of years to complete a broad cycle. Because of precession, different stars have stood near the celestial pole in different historical eras. Polaris is well placed for observers in the present age, but it was not equally close to the pole for every traveler in the distant past. The North Star offers more than direction. Its height above a level northern horizon gives an approximate measure of latitude. Latitude is distance north or south of the equator. Near the equator, Polaris appears low, close to the northern horizon. Farther north, it stands higher. At the North Pole, it would appear almost directly overhead. A navigator could measure this height, also called the star's altitude, and estimate how far north a vessel had traveled. The underlying observation was beautifully plain. As a traveler moved north or south, the familiar star appeared to rise or lower in the sky. But Polaris belongs mainly to northern skies. It cannot be seen from much of the southern hemisphere because it lies below the horizon. Southern navigators therefore learn to use other patterns. They watched the rising and setting positions of particular stars, recognized groups of stars, and followed their changing places as the night and the seasons passed. A star rising at a known point on the horizon could help a navigator hold a direction for a time. As it climbed and moved away from its useful position, another familiar star could become the guide. In this way, the sky could be remembered as a sequence of directions, each one appearing in its own time. People also connected stars with mountain peaks, islands, seasons, winds, and currents. Their systems differed according to latitude, landscape, and tradition. What worked beneath one sky could not always be carried unchanged into another. A northern traveler entering unfamiliar southern waters might search in vain for a trusted star. Anyone far from familiar country would need to learn new patterns and a new relationship between stars and horizon. The sky, then, was reliable, but it required knowledge and patience. A navigator needed to know which heavenly body was being observed, how it moved, and how the season affected its place. To determine position more precisely, the date and time could also become important. A clear view of the horizon was often needed because the height of a star or the sun was measured from that level line where sea and sky seemed to meet. At sea, celestial observations eventually made latitude easier to estimate than longitude. Longitude is distance east or west around Earth. If latitude can be imagined as a set of horizontal bands around the globe, longitude can be imagined as a series of lines running from pole to pole. Finding longitude was difficult because east-west position is closely connected to time. Earth turns at a steady rate, so a difference in local time corresponds to a difference in longitude. A navigator who knew the precise time at a chosen reference place could compare it with local solar time. But preserving that reference time during a long voyage required a sufficiently accurate clock. It also had to continue working through the motion of a ship, damp air, and changing temperatures. Without such a clock, longitude depended on complex astronomical methods or less certain estimates. No single observation solved every problem. Even an experienced navigator could find the sky hidden by cloud. The horizon might vanish into mist. A vessel might roll beneath an uneven sea, making angles difficult to measure. Sometimes only a brief opening between clouds allowed the sun or a familiar star to be seen. When that opening came, the navigator watched carefully, and when it did not come, the navigator waited. The journey did not simply end. Winds still had direction. Ocean swells carried the memory of distant weather. Dead reckoning could carry an estimate forward. In dead reckoning, a navigator began from a known or estimated position, then considered the vessel's course, speed, and the time spent traveling. The result was not perfect, but it offered continuity when the heavens were hidden. In shallower water, soundings could reveal depth and sometimes the character of the seabed. Currents, birds, floating plants, coastal sounds, and local knowledge all added their quiet evidence. Navigation remained what it had always been, the patient gathering of signs. The compass, when it later joined the navigator's collection of tools, did not replace these older forms of attention. It complemented them. The sky could help test the direction shown by a compass, and the compass could provide guidance when the sky was obscured. Each method supported the other, just as a remembered coastline might support a reading of the stars. Now a bank of cloud moves across the evening horizon. One bright star disappears, then another. Their reflections fade from the water. For a while the navigator waits beneath the dim sky, listening to the wind and watching the long rhythm of the sea. Direction is still present, though it cannot be read from a single sign. Beyond the cloud, the stars continue their measured circles. The sun will return to the eastern sky. Shadows will shorten and lengthen again. Yet when the heavens are hidden, the question of direction remains. In the quiet shelter of a room, or perhaps within a ship's wooden cabin, attention will soon turn away from the clouded sky. It will settle instead upon a small dark stone with an unexpected property. Chapter 3. A Curious Stone. In the quiet shelter of a small room, a dark stone rests in an open palm. It is heavier than its size might suggest. Its surface is uneven, with dull black ridges that catch the lamplight. At first, there seems to be nothing remarkable about it. It does not shine like a jewel or carry the delicate pattern of a shell. It resembles countless other stones gathered from dark earth and rocky hillsides. But when a small piece of iron is brought near, something unexpected happens. The iron shifts. Perhaps it is only a narrow pin lying on a wooden table. As the stone approaches, the pin trembles, turns slightly, and slides across the grain. It touches the stone and remains there, held by a force that cannot be seen. The dark stone is a lodestone, a naturally magnetized material that is usually magnetite. Magnetite is an iron oxide, meaning that it is a substance made from iron and oxygen. It occurs naturally in many places, although not every piece has strong magnetic properties. An ordinary piece of magnetite may show little useful attraction. A lodestone is unusual because it has become naturally magnetized strongly enough to attract iron. Long before people knew the modern scientific language of atoms, forces, and magnetic fields, they could observe this simple behavior. A stone drew iron toward itself. The effect required no flame, string, flowing water, or visible hand. It worked in sunlight and lamplight, in silence, and even through a thin layer of cloth. To anyone encountering it for the first time, the stone must have seemed quietly strange. Knowledge of magnetic stones appeared in more than one part of the ancient world. Writings from ancient China refer to stones that could attract iron. Greek and Roman writers also discussed magnetic attraction. These records tell us that people separated by great distances had noticed the same natural property. The precise beginnings remain uncertain. Ordinary discoveries are not always written down at the moment they occur. A miner may notice that iron tools cling to a particular rock. A craft worker may find that iron filings gather around a dark stone. A trader may carry the object to a market, where others handle it and ask questions. Years or even centuries can pass before an observation enters a text that survives. This uncertainty leaves room for traditional tales. One old legend tells of a shepherd whose iron-tipped staff, or perhaps the nails in his sandals, were pulled toward magnetic ground. Versions of the story differ, as legends often do. It offers a memorable picture, but it is not a secure historical account of how magnetism was discovered. The word magnet has traditionally been connected with magnesia, an ancient place name associated with regions in the Greek world. Yet the history of words can be as winding as the history of objects. Spellings change. Similar place names may become entangled. The traditional link is worth remembering, but it does not identify one person, one stone, or one dramatic moment of discovery. The compass did not appear in such a moment. No known individual simply lifted a lodestone and invented magnetic navigation. The instrument developed gradually through observation, experimentation, comparison, and practical improvement. The first observation was attraction. A lodestone could draw a suitable piece of iron toward itself. It could also give magnetic properties to certain objects made from iron or steel. To magnetize an object means to give it magnetic properties so that it begins to behave like a magnet. A slender needle, for example, could be stroked against a lodestone in a careful and repeated way. Afterward, it might attract tiny scraps of iron. More importantly for the future compass, it might respond to the larger magnetic influence surrounding Earth. Yet attraction alone does not make a compass. Imagine a lodestone lying flat upon a table. It may pull at a nearby pin, but because the stone cannot move, it reveals no preferred direction. Even a magnetized needle, placed firmly beneath a weight, will tell a traveler nothing. Its magnetic properties are present, but it has no freedom to answer the influence around it. For directional behavior to become apparent, the magnetic object must be able to turn freely. It might be floated upon water, supported by a small piece of cork, wood, or reed. It might be hung from a fine thread. It might be balanced carefully on a point, or placed on a pivot, a support that allows it to rotate. When friction is low and the object can move, it turns, hesitates, and eventually settles along a repeated line. This is the quiet step that separates a curious attracting stone from the beginning of a direction finder. The movement does not mean that the needle sees a distant mountain, nor does it point like an arrow toward one exact object beyond the horizon. Instead, it responds to Earth's magnetic field. A magnetic field is an invisible pattern of influence around a magnet. It cannot be watched directly in the way one watches a stream flowing between its banks, but its effects can be observed. Iron filings placed near a magnet arrange themselves in patterns. A freely turning needle changes its position. These movements reveal that an influence is present in the space around the magnetic object. Earth itself has a vast magnetic field. Near the planet's surface, part of that field lies along the horizontal plane, the level plane of the ground or of still water. A compass aligns with this local horizontal part of Earth's magnetic field. In simple terms, the needle settles along a broadly north and south line because of the magnetic conditions in the place where it is being used. This direction is useful, but it is not quite as simple as a needle pointing toward a single fixed target. Earth's magnetic field varies from region to region and changes gradually through time. Later navigators would learn that magnetic north and geographic north are not always exactly the same. For now, it is enough to picture the needle responding to an immense and invisible pattern surrounding the world. Ancient observers did not need a modern explanation in order to notice a repeated result. Practical knowledge often begins before the deeper cause is understood. People recognized the rhythms of the seasons before they understood Earth's orbit. They followed tides before they could describe the influence of the moon in mathematical terms. In the same way, a magnetic object could become useful while the nature of magnetism remained mysterious. Still, the surviving evidence must be handled with care. Greek and Roman writers clearly knew that certain stones attracted iron. Some authors wondered about the force, while others used magnetic attraction as an image in philosophy or poetry. But knowing that lodestone attracts iron is not the same as using magnetism to find direction. Surviving evidence does not show that the classical Mediterranean world used a magnetic direction finder. The distinction is small in words, yet large in practice. A person can know that a lodestone lifts an iron ring without ever testing whether a magnetized needle settles along a repeated line. Even if the turning is noticed, it may first be treated as a curiosity rather than a guide. Then someone must compare the needle with the sun, the stars, a familiar road, or the orientation of a building. The behavior must be tested again, at different hours and perhaps in different places. Only then can the repeated direction begin to carry practical meaning. History often advances through such quiet comparisons. Someone watches the needle, someone else repeats the test. A craft worker finds a smoother support. A scholar records the observation. A traveler wonders whether the result remains dependable beneath a cloudy sky. None of these steps alone produces the finished compass, yet each one helps prepare the path toward it. In ancient China, magnetism became part of a culture already deeply attentive to direction and the arrangement of space. North, south, east, and west could carry practical, ceremonial, and symbolic meaning. Buildings, seats, roads, and landscapes might be considered in relation to orientation. Within such traditions, the directional behavior of a magnetic object could become more than a curious trick. The earliest details are not always easy to interpret. Some old texts describe objects or practices whose exact construction remains uncertain. Devices mentioned in literature may be known only through copies made much later. Reconstructions by modern historians can demonstrate what might have worked, but a successful reconstruction does not prove that every ancient device was built in precisely that way. And so the story must move gently among what is firmly recorded, what appears likely, and what remains uncertain. The natural foundation is clear. Magnetite exists. Some pieces of it are naturally magnetized and become lodestones. Lodestones attract iron, and they can magnetize suitable objects made from iron or steel. A magnetic object, when allowed to turn freely, can align itself in response to Earth's magnetic field. Upon these simple facts, many designs could eventually be built. Consider the table once more. Under the lamplight, the dark lodestone lies beside a slender iron needle. The needle is ordinary in appearance, made for cloth and thread rather than travel. A hand lifts it and draws it slowly along the stone. The movement is repeated in the same direction, patiently and without haste. Then the needle is tested. At first, it may cling faintly to a tiny scrap of iron. This suggests that it has acquired magnetic properties, but another test is needed. The needle must be released from the grip of the hand and from the resistance of the tabletop. A fine thread might suspend it. A sliver of reed might carry it upon water. A smooth support might allow it to balance and turn. Each method reduces the forces that would otherwise hold the needle still, allowing Earth's much quieter influence to become visible. In a shallow bowl, the water is calm. Lamplight forms a pale oval upon its surface. A light piece of wood or reed floats near the center, carrying the magnetized needle. Small ripples spread toward the rim and slowly fade. For a moment, the needle seems uncertain. It turns a little in one direction, pauses, and moves back. It passes the line where it will finally rest, then returns once more. Each movement is smaller than the last. At length the water grows still, and the needle settles. If the floating support is turned gently by hand and then released, the needle slowly comes back toward the same line. The test can be repeated. What first seemed like restless movement begins to appear orderly. There is no need for the needle to understand the field that guides it. There is no need for the observer to possess a complete explanation. It is enough at first to notice the return, the same direction, again and again. Such a result invites patience. The observer may wait for the water to settle, then turn the floating support once more. The needle wanders and returns. It may quiver when someone crosses the floor, or when a breath of air touches the water. Yet when the disturbance passes, it seeks its resting line again. The attracting stone has opened a new question. If a freely turning magnetic object repeatedly settles in one direction, what might that direction mean? How might it be named, tested, and woven into older knowledge of roads, seasons, buildings, winds, and stars? The answer did not arrive all at once. A stone that attracts iron is not yet a compass. A magnetized needle that turns is not yet a complete navigational instrument. The behavior must be observed, understood in practical terms, and joined with ways of marking direction. Supports must become steadier. Movement must become easier. The result must become clear enough to read. Each improvement would come through human hands and patient attention. In ancient China, this question became connected with long traditions of orientation, ceremony, and the ordering of space. There, accounts would emerge of a directional object shaped not like a modern needle, but like a spoon resting upon a smooth surface. Some details would remain uncertain, while others would become clearer through surviving texts and later study. For now, the small needle remains upon the water. The hand withdraws. The room grows quiet again. Beside the bowl, the dark lodestone rests where it was placed, plain and heavy beneath the steady light. The last ripples disappear. The magnetized needle quivers once, almost too slightly to see, and returns to its quiet direction. Chapter 4. The South-Pointing Spoon. In a quiet courtyard, morning light falls across smooth paving stones. Wooden doors open toward a carefully chosen direction. Beyond them, tiled roofs form orderly lines, and the spaces between buildings seem to gather the sunlight and guide the passing air. To someone entering the courtyard, its arrangement may feel simple and natural. Yet the placement of a doorway, a hall, or an altar can carry meaning. Direction is not always treated as a set of empty lines drawn across the land. It may be connected with season, ceremony, authority, balance, and a culture's understanding of how human life belongs within a larger world. In several Chinese systems of orientation, south held particular importance. A ruler might traditionally face south, looking toward warmth and light, while attendants faced north. Maps and diagrams were not always arranged with north at the top, as many modern readers expect. South could occupy the honored or guiding position. For this reason, early Chinese directional objects were often described as pointing south rather than north. A magnetic object aligns itself along a north and south line, so either end may be treated as the named pointer. The choice depends upon custom, design, and the meaning given to each direction. This is why the term Sinan is commonly translated as south pointer. It belongs to the earliest clear documentary tradition associated with the compass, a tradition that comes from China. Early Chinese writings refer to magnetic attraction, and some describe objects connected with the indication of south. Yet the path from these old words to a familiar instrument is not perfectly straight. Texts may survive in copies made across many generations. Words can change in meaning. A brief sentence that seemed clear to its first readers may become difficult centuries later, when the objects and practices it described are no longer present. The most famous image associated with the Sinan is a spoon made from lodestone. Lodestone is a naturally magnetic iron-bearing mineral. In modern illustrations and museum displays, the spoon usually rests upon a smooth, polished plate. Its rounded bowl touches the surface, while its narrow handle extends outward. If the spoon can turn with little resistance, the handle is expected to settle toward the south. The image is graceful. The broad plate may be marked with directions and other divisions, while the dark spoon rests near its center. A light touch sets it moving. It turns slowly, pauses, and then shifts once more before coming to rest. This spoon-shaped device is associated with traditions from the Han period, more than 2,000 years ago. But it is important to approach the image with care. No ancient lodestone spoon has been securely identified through archaeology. No recovered object allows historians simply to place it on a table and say, without doubt, that this is the instrument described in the early writings. Instead, the famous spoon is a reconstruction. A reconstruction is an attempt to make or imagine an earlier object by using the evidence that remains. Researchers may study written descriptions, surviving images, known materials, later instruments, and the practical needs of the device. They then create something that might resemble the original. A reconstruction can teach us a great deal. It can show whether an idea is physically possible. It can reveal where an ancient maker might have faced difficulties. Yet it is not the same as an ancient artifact. It is a careful proposal, a bridge built from fragments of evidence. Modern researchers have shaped lodestone into spoons and placed them on polished plates. Under suitable conditions, some of these reconstructions have turned and aligned themselves. This shows that a spoon-shaped magnetic pointer can work. It does not by itself prove that every early reference to a south pointer describes such a spoon, or that these devices were widely used in one standard form. The practical difficulties are easy to imagine. A spoon must be balanced well enough to turn. If one side presses too heavily against the plate, friction may hold it still. Friction is the resistance that occurs when two surfaces move against one another. Even a small rough place can matter when the magnetic force is gentle. The plate must be smooth, and the spoon's rounded base must make only a small area of contact. The stone itself must have enough magnetic strength. Lodestones vary. One piece may pull firmly at iron, while another is much weaker. Shaping the mineral can also be difficult, and the finished spoon must retain enough magnetism to overcome its own weight and the drag of the surface beneath it. A slight tilt in the plate might influence the movement. Dust could slow it. An uneven spoon might favor one resting position for reasons having nothing to do with direction. Nearby iron might disturb the result. A reconstruction could work beautifully after careful preparation, yet perform poorly under less favorable conditions. These difficulties do not make the reconstruction meaningless. Instead, they help historians ask more precise questions. How smooth did the plate need to be? How strong would the lodestone need to become? Was such an object used often, or only on special occasions? Did the early words refer to a spoon at all, or to another kind of pointer? The wording and meaning of the surviving texts remain debated. Scholars compare passages, study the history of particular terms, and consider the settings in which the objects were mentioned. The spoon form remains plausible and deeply influential, but it is not an uncontested artifact preserved from antiquity. Historical uncertainty can feel like mist above a distant field. It does not erase the landscape. It simply asks the traveler to move patiently, noticing which shapes are firm and which remain partly hidden. What does appear clear is that magnetic behavior became connected in China with ideas of direction and ordered space. If early south-pointing magnetic devices were used, they may not have been ordinary tools for travelers or sailors. Their settings may instead have included divination, geomancy, ceremonial orientation, or the selection of sites. Divination is a traditional practice of seeking guidance or meaning through interpretation. Many cultures have developed forms of it, using patterns, natural signs, carefully arranged objects, or established systems of symbols. Its purpose is not always to predict a single future event. It may also help people consider decisions, understand circumstances, or place an action within a meaningful order. Geomancy is the traditional interpretation of place, direction, and landscape. In a broad sense, it considers how a building, tomb, road, or settlement relates to the surrounding land. Direction is understood not in isolation, but as part of the character and arrangement of a place. A directional instrument used in such a setting would offer more than a simple answer to the question, which way should I walk? It might help orient a structure, arrange a ceremonial space, or compare the features of a site with a larger system of meaning. Some diviners' boards and later geomantic compasses carried markings far more complex than the four familiar cardinal directions of north, south, east, and west. Their surfaces could be divided into rings, sectors, signs, and categories. These markings expressed relationships among direction, time, natural cycles, and human activity. Such designs reflected cosmology. Cosmology means an organized understanding of the universe and its order. Today, the word may suggest the scientific study of the universe. In a historical and cultural setting, it can also refer more broadly to a system explaining how the heavens, the earth, the seasons, the directions, and human affairs belong together. On an instrument shaped by such ideas, direction was one thread in a much larger woven pattern. A pointer settling towards south could become part of an ordered surface filled with signs and relationships. The movement itself might be small, but the world of meaning around it could be broad. It is useful, too, to distinguish the magnetic south pointer from another famous Chinese device, the south-pointing chariot. Historical descriptions and later reconstructions of this chariot tell of a wheeled vehicle carrying a figure whose outstretched arm continued to indicate a preset direction as the vehicle turned. Despite its name, the south-pointing chariot should not be confused with a magnetic compass. The descriptions concern a mechanical system that used the motion of wheels and arrangements of gears. The principle is rather like keeping count of how far one wheel turns compared with the other. When the chariot changes direction, its wheels travel different distances. A carefully designed mechanism can use that difference to rotate the pointing figure in the opposite way. In this manner, the figure's arm may continue to indicate the direction that was established at the beginning. But the chariot must begin with a direction already known. It does not independently discover south after being carried to a new place. It maintains a preset direction through mechanical motion. Uneven ground, slipping wheels, and accumulated errors could also cause the indication to drift. It was an ingenious idea, but it answered a different question. The chariot attempted to preserve a direction after that direction had been chosen. A magnetic pointer, by contrast, could align itself again after being moved, provided that it remained free to turn. The lodestone spoon, if it was used in the form commonly reconstructed, would not need to count the turning of wheels. Its motion would arise from magnetism and from the delicate freedom of its rounded base upon the plate. And so the story returns to a simple requirement that runs quietly through the history of the compass. The directional object must be able to move. A lodestone may possess magnetic strength, yet remain silent when held firmly in the hand. A spoon may carry the same tendency, yet reveal nothing if friction binds it to a rough surface. Only when the object is balanced and released can its preference become visible. The challenge is gentle but exacting. The pointer must be supported, but not trapped. It must be steady enough to read, yet free enough to respond. Too much resistance hides the motion. Too little control allows the object to wander. Between those conditions lies the quiet possibility of direction. In the courtyard, the day has moved on. Sunlight now reaches a different edge of the paving stones. Shadows have shortened and begun to lengthen again. The open doors still hold their chosen alignment, while a soft current of air passes beneath the tiled eaves. On a low table rests a polished plate, its surface divided into meaningful regions. At the center is a dark spoon, carefully shaped and balanced. We cannot know that an ancient scene looked exactly like this. The plate may have been different. The pointer may have taken another form. The surviving words may preserve practices that changed across centuries. The familiar spoon belongs partly to old texts and partly to later interpretation, experiment, and imagination. Even so, the image gathers several ideas that are securely part of the story. People in ancient China observed magnetic attraction. They gave close attention to direction and ordered space. South held particular importance in several systems of orientation. And at some point, magnetic behavior became associated with objects that indicated a direction. The uncertainties do not leave the scene empty. They allow room for patient questions. Perhaps a device like this was used in a ceremonial setting. Perhaps it helped with the interpretation of a place. Perhaps the object described in an early text had another form entirely. The evidence does not yet permit one simple answer. History often reaches us in this way. A few words remain, while the hands that wrote them are gone. An object is described, but the object itself has not survived. Later generations read, compare, rebuild, and test. Some possibilities become stronger, others fade. The work continues slowly without the need to force every uncertainty into certainty. For now, the imagined plate remains upon the low table. Its markings wait in stillness. The dark spoon rests at the center. A hand reaches forward and gives it a measured touch. The spoon glides across the polished surface. At first, the handle passes one marking, then another. Its movement grows slower. Friction gently takes away the motion, while the magnetic stone favors one line above the others. There's a pause. The spoon shifts once more, almost too slightly to see. Then it settles into quiet. Whether on a polished plate or in some other arrangement, a magnetic object had to move freely before its directional tendency could be seen. The next practical step would be smaller, lighter, and more delicate. A magnetized needle carried by water or suspended from a thread. Chapter 5. The needle learns to float. Beneath a sheltered roof, away from the passing wind, a shallow bowl rests upon a wooden table. Its water is clear and still. Soft daylight falls across the surface, where the pale reflection of a beam stretches quietly from one side to the other. Beside the bowl lies a slender needle. It is much smaller and lighter than the dark magnetic spoon of earlier centuries. Because it weighs so little, it can respond to forces too gentle to turn a heavier object easily. Yet, before the needle can reveal a direction, it must first be prepared. An ordinary piece of iron or steel does not always behave like a compass needle. To give it a magnetic tendency, it can be rubbed with lodestone, the naturally magnetized stone that people had observed for many generations. The stone is moved along the needle with care. After this has been repeated, the needle may begin to behave differently. When the lodestone is taken away, the needle can retain some of its magnetism. This retained magnetism is called remanence. The word means quite simply what remains. Steel generally retains magnetization better than soft iron, although pre-modern materials varied greatly. One needle might work well, while another, made by a different craftsperson or treated in a different way, might gradually lose its strength. Knowledge of magnetism was therefore joined to knowledge of metal. The material, the method, and the care of the maker all mattered. Once magnetized, the needle must be allowed to turn freely. It might be hung from a very fine thread. This is a form of suspension, meaning that the needle is supported while remaining free to move. If the thread is light and does not twist too strongly, the needle can swing gently, slow down, and settle along an approximately north to south direction. There is another method, well suited to the waiting bowl. The needle could be passed through a short piece of reed, laid upon a small chip of wood, or attached to another light support. Cork could also serve this purpose. Whatever the material, the support must be buoyant. Buoyant simply means able to float. The needle and its support are lowered gently onto the water. Small circles spread outward and touch the sides of the bowl. For a moment, the little float drifts with them. Then the circles fade, and the surface grows quiet again. Freed from the drag of a table or polished plate, the needle begins to turn. It requires no gears. No hand guides it toward a painted mark. The water supports its weight, while Earth's magnetic field gives it a preferred alignment. The movement may be slow enough to follow with the eye. There is a slight drifting, a pause, and then another small turn. At last, one end points approximately north, while the other points approximately south. The arrangement is simple, yet it gathers together several older kinds of knowledge. People already knew how to work iron and steel, how to shape slender needles, and how to recognize lodestone. They knew that light objects could be floated on water. They also knew that direction mattered in travel, military movement, and the ordering of places. The floating needle joined these understandings in a delicate and useful form. An intriguing description occurs in a Chinese military work completed in 1044. It tells of a south-pointing fish used for orientation. The fish seems to have been a thin piece of iron, shaped and treated so that it could indicate direction when placed in water. It is a memorable image. A small metal fish floats in a bowl, slowly turning until its head or tail favors the south. Yet the description must be approached with care. Historians still interpret the details of how the fish was magnetized, how it was made, and how accurately it worked. Old technical accounts can be brief. A writer may assume that readers already understand part of a process. Meanings may also become less certain as texts are copied, preserved, and studied across many centuries. The south-pointing fish is not evidence of a single person suddenly creating a complete mariner's compass. It is better understood as part of continuing experimentation with magnetic orientation. People were exploring how iron could acquire a directional tendency, and how water could allow a light object to turn. A few decades later, the surviving evidence becomes clearer. Around 1088, the Chinese scholar Shen Kuo completed a remarkable collection of writings now known in English as the Dream Pool Essays. Shen Kuo was a government official, diplomat, and attentive observer of the world around him. Among the many subjects he examined was the behavior of magnetized needles. Shen Kuo did not invent the compass, nor should he be imagined working entirely alone, revealing a device unknown to everyone else. His writing shows that magnetized needles and methods of supporting them were already known. His importance lies in the care with which he documented and investigated these practices. He discussed several ways to support a needle so that it could turn. It might float on water. It might rest in an arrangement that reduced friction. It could also be suspended from a fine thread, allowing it to swing before settling. Each method had its own character. Water was simple and readily available, but it was rarely perfectly still. A breath could trouble the surface. Small currents within the bowl could move the floating support. On a ship, the deck rose and fell and the water moved with it. A fine thread avoided some of these difficulties, yet the thread itself could twist and influence the needle. The craft of making a compass was therefore not only a matter of discovering that a needle could point, it also involved the patient work of allowing it to point reliably. Shen Kuo recorded another observation of great importance. A magnetic needle did not align exactly with the north to south line established through astronomical observation. Astronomical north is true north as determined from the sky and Earth's axis of rotation. Magnetic north, by contrast, is the direction favored by a compass needle under the influence of Earth's magnetic field. The two directions are often close, but they are not identical. One may imagine two fine lines drawn across a sheet of paper. Both extend generally north and south, yet one is turned slightly to the side of the other. The angle between those lines is called magnetic declination. Shen Kuo's writing provides an early, clear recognition of this difference. Such an observation required patience. A needle does not always present its answer immediately. It may tremble, sway, or be disturbed by the material supporting it. To notice a consistent difference between magnetic direction and astronomical direction, an observer must compare one method with another. A single hurried glance is not enough. This was an important step in understanding the instrument. The needle was useful, but it was not perfect. Magnetic north and true north were not precisely the same, and careful navigation depended upon recognizing which direction the instrument revealed. From the sheltered bowl, the story moves slowly toward the coast. In the early 12th century, the writer Zhu Yu described the practices of mariners. His work, the Pingzhou Table Talks, was written in that period and published in 1119. Within it is clear evidence that sailors used a magnetic needle when clouds concealed the familiar guidance of the sun and stars. Imagine a wooden vessel moving beneath a broad gray sky. Rain has softened the horizon, the coastline is hidden, and the daylight offers no clear shadow. When night arrives, the clouds remain, covering the stars that would otherwise help the crew recognize their direction. In such weather, a magnetic needle offers a quiet line through the uncertainty. A sailor brings out the small instrument and shelters it as well as possible. If the needle floats in a bowl, the sailor waits for the water to settle. The float turns with the movement of the ship. Ripples pass beneath it. The needle circles a little, slows, and then moves once more. Between one motion and the next, its repeated tendency becomes visible. Although disturbed, it returns toward the same general alignment. Zhu Yu's account does not describe sailors abandoning every older skill in favor of the magnetic needle. Instead, it presents navigation as a layered practice. Mariners knew geography through experience. By night, they observed the stars. By day, they used the sun. When the sky was overcast and those guides were hidden, they turned to the needle. The compass joined navigation. It did not replace it. A compass gives direction, but it does not give position. It can show which way lies north or south, yet it cannot tell a sailor which bay waits beyond the mist. It cannot say how far the vessel has traveled, how quickly it is moving, or how deep the water is beneath the hull. For these questions, mariners continued to rely upon remembered routes and local knowledge. They estimated distance and speed. They watched for landmarks whenever the coast became visible. They used celestial observations when the sky was clear. They took soundings to learn the depth of the water, and they consulted charts where charts were available. The magnetic needle became one aid among many. This helps explain how the floating needle could be both delicate and important. It did not need to answer every question. It only needed to preserve a sense of direction when other signs had faded. Beneath cloud, rain, or haze, that single piece of information could support a navigator who already understood the route. The instrument still demanded calm handling. Water sloshing from side to side could keep the needle moving. Small currents within the bowl could carry the float. The rising and falling of a ship could disturb the surface again and again. Even when the water appeared still, the vessel itself might be turning beneath it. A sailor could not always trust one quick glance. It was better to wait, observe repeated movements, and compare what the needle showed with everything else that was known. The instrument became useful through the same habits that had guided travelers for generations. Patience, memory, experience, and attention remained essential. There is something gentle in that continuity. A new tool did not erase the knowledge that came before it. The sun still crossed the daytime sky, stars still appeared at night. Coastlines, routes, soundings, and remembered distances still mattered. The needle simply remained available for the hours when rain drew a curtain over the heavens. The shallow bowl has been left undisturbed. The last ripples diminish into faint lines and disappear against its edge. The reed rests lightly upon the surface. The needle holds its quiet direction, not perfectly and not without conditions, but steadily enough to be of service. Nearby, a hand may be waiting to lift the bowl or carry the knowledge elsewhere. For a useful technique rarely remains still. It travels in memory, in conversation, in copied texts, and sometimes in the hands of sailors moving from one harbor to another. Chapter 6. Knowledge Along Roads and Seas. At dusk, a harbor gathers the colors of both land and water. The last sunlight rests on tiled roofs and folded sails. Wooden hulls rise and settle beside the quay, making small sounds against their ropes. In the market nearby, baskets are carried ashore, jars are counted, and lengths of cloth are unrolled beneath shaded awnings. Many languages pass through such a place. Sailors ask for water. Merchants discuss weights and prices. Pilots speak of shoals, winds, and currents. A craftsperson examines a broken fitting, turning it carefully in the lamplight. Some conversations concern valuable cargo. Others carry knowledge that has no visible weight at all. A practical technique may pass from one person to another in only a few gestures. A sailor strokes an iron needle with a magnetized stone. He lays it across a sliver of reed, then lowers it gently onto water. The reed drifts for a moment. Then it turns. Those watching understand the important part, even if they do not share every word. This is one way practical knowledge travels. Historians sometimes call the process transmission. Transmission is simply the movement of ideas, skills, or objects from one person or region to another. Yet transmission rarely leaves a clear path behind it. A merchant may learn a method without writing it down. A sailor may demonstrate it in one port, then continue onward with the next tide. A craftsperson may alter the design, making it better suited to local materials. Years later, the adapted instrument may seem to belong entirely to its new home. The first surviving written description of a practice is therefore not necessarily the moment when the practice began. It is only the earliest description that has reached us. Earlier documents may have been lost. The knowledge may have been carried in memory rather than on paper. It may have been so familiar to those using it that no one thought it necessary to explain. A needle could travel in a small box. A technique could travel in the hands. China provides the earliest clear documentary tradition for magnetic direction finding. Chinese writings record long attention to lodestone, magnetized objects, and pointers that align themselves with direction. Over time, these observations became connected with travel and navigation. But when similar forms of the compass appeared in Europe and in societies of the Islamic world within the following centuries, the route between them was not recorded as one continuous journey. No surviving account allows us to follow the idea from workshop to vessel, from harbor to harbor, and from one language into another. There were many possible channels. Ships crossed the Indian Ocean, following seasonal winds between East Africa, Arabia, India, Southeast Asia, and China. Goods moved through the Persian Gulf and the Red Sea. Ports in India and Southeast Asia welcomed crews from distant coasts. Overland roads joined towns, caravan stations, and centers of scholarship. Diplomatic visitors carried gifts and observations. Sailors sometimes changed vessels. Craftspeople moved to places where their skills were needed. Scholars translated works from one language into another, sometimes adding comments drawn from their own experience. Through these networks moved silk, ceramics, spices, metalwork, maps, stories, mathematical methods, and ways of observing the heavens. Knowledge of magnetic direction may also have traveled along one or several of these paths. Yet the evidence does not support a simple tale in which one named traveler carried one compass directly from China to Europe. History is quieter and more intricate than that. A method might move gradually. It might be forgotten in one place and adapted in another. It could travel without its original name. A listener might remember only the essential action: touch the iron to the magnetic stone, give it room to turn, and watch where it settles. Once the magnetic properties of lodestone and iron were known, people in more than one region could also have recreated a simple magnetic pointer for themselves. Independent invention, local adaptation, and transmission through contact are not mutually exclusive possibilities. More than one of them may have taken part in the life of this useful idea. In Europe, one of the earliest well-known compass descriptions is associated with Alexander Neckham, an English scholar of the late 12th century. Neckham wrote of mariners using a magnetized needle when clouds concealed the stars. His account is brief, but it suggests that the technique was already understood by sailors. It may not have been new to them at all. By the time a scholar mentions a tool in writing, working people may have used it for years. Imagine an overcast sea beneath a pale, unbroken sky. Familiar stars are hidden. The horizon remains visible, but it offers no certain north or south. A magnetized needle is allowed to settle. It provides one steady reference, not replacing all that the navigator knows, but helping when the sky is silent. The mariner still observes the wind and waves. He remembers the coast and the vessel's course. He measures progress as well as he can. The needle adds one quiet piece of information to everything else. Several generations later, in 1269, a scholar often known as Petrus Peregrinus wrote a detailed European study of magnets. An organized written study of a subject is called a treatise. Rather than mentioning magnetic instruments only in passing, Petrus examined their behavior carefully. He described both floating and pivoting forms. A floating needle rests on something light upon water. A pivoting needle balances on a fine point, allowing it to turn freely. A pivot is simply a fixed point around which an object rotates. A door turns on its hinges. A wheel turns around an axle. In much the same way, a compass needle can turn around its pivot until it settles along its magnetic direction. The pivot would eventually become especially important aboard ships. Water in a bowl could spill or slosh as a vessel moved. A balanced needle protected within a case offered the possibility of a steadier instrument, but that development was gradual, shaped by repeated experiments in workshops and aboard vessels. Written descriptions such as those of Neckham and Petrus give historians firm places to pause. Still, they do not reveal every step that came before them. Between one surviving text and the next lie countless ordinary moments: a sailor demonstrating a needle, a craftsperson changing its support, or a scholar comparing its direction with the sky. Farther south and east, surviving writings offer other distinct glimpses. It is helpful to remember that the phrase "the Islamic world" describes many societies, languages, places, and traditions. It does not refer to a single uniform culture. It includes communities across broad regions, linked in various ways by religion, learning, trade, and travel, yet each shaped by its own local history. A secure Persian account describes a south-pointing iron fish used during a voyage in 1232 and 1233. The fish form recalls other ways of shaping magnetic pointers into familiar objects. Floating on water, the magnetized iron could turn and indicate direction. The image is simple. A small iron fish rests on the surface of a bowl. The vessel moves over open water, while the pointer within the bowl moves more gently. After wavering, it settles toward its accustomed direction. Another work, written in 1282, looks back upon a voyage between Syria and Egypt in 1242 and 1243. It describes a needle placed with a reed and floated on water. The same work also mentions floating iron fish in the Indian Ocean. These details suggest a world of varied instruments rather than one fixed design. In one place, a pointer might be shaped like a fish. In another, an ordinary needle could lie across a reed. The materials were simple enough to be found aboard a vessel or in a workshop. What mattered was the careful preparation of the iron and its freedom to turn. These writings also connect different waters. The voyage between Syria and Egypt belongs to the eastern Mediterranean world, while the mention of floating iron fish reaches toward the Indian Ocean. Ports along these seas form parts of broad networks through which mariners exchange sailing directions, weather knowledge, measurements, stories, and practical devices. Perhaps a technique was demonstrated beside a cargo of spice or cloth. Perhaps it was discussed while a vessel waited for a favorable wind. Perhaps a sailor learned it far from home, then reproduced it years later with a different kind of reed or a differently shaped piece of iron. Such moments usually disappear from the written record. Their absence does not prove that they occurred, but it reminds us why certainty is difficult. Practical knowledge can spread informally, unevenly, and without leaving a paper trail. Magnetic instruments also served purposes beyond steering ships. Around 1290 to 1300, astronomical writings from Yemen and Egypt describe magnetic instruments used in finding the meridian and the Qibla. A meridian is a north-south line. In astronomy, it can be imagined as a great line passing from north upward through the point directly overhead and then down towards south. Knowing this line helped observers organize the sky, position instruments, and make measurements. The Qibla is the direction toward Mecca used in Islamic prayer. Because Muslim communities lived across many lands, determining that direction could involve geography, astronomy, and mathematics. The sun and stars provided valuable guidance. A magnetic instrument offered another way of approaching the question, especially when combined with local knowledge and careful calculation. Here the compass belonged not only on the deck of a ship but also within the thoughtful work of astronomers and religious scholars. A turning needle could help orient an observer's instruments, just as it helped orient a vessel. Its purpose depended upon its setting. On a coastline, it could assist a mariner when clouds covered the sky. In a courtyard or study, it could help establish a north-south line. In the work of finding the Qibla, it could contribute directional information to a question joined with religious practice. The same physical behavior, an iron pointer turning under the influence of Earth's magnetism, could therefore become useful in several different traditions of knowledge, and the many societies of the Islamic world. Documented compass forms appear within a span of a few centuries. It is tempting to arrange every account into a single line, as though a needle itself had drawn the route. But the pattern is more like the harbor at dusk, where roads, rivers, and sea lanes meet without becoming one road. Perhaps some navigators learned magnetic methods through Indian Ocean trade. Perhaps knowledge passed through ports in Southeast Asia, India, the Persian Gulf, or the Red Sea. Overland trade and diplomatic contact may also have mattered. Sailors, merchants, craftspeople, diplomats, and scholars may each have carried some part of the idea. Some communities may have received an existing technique and changed it. Others, already familiar with magnetic properties, may have devised a pointer of their own. Still others may have combined a newly encountered method with practices they already knew. The possibilities do not have to compete. Contact can inspire adaptation. Adaptation can resemble invention. An independently made instrument can later be improved by knowledge arriving from elsewhere. There is no need to turn this history into a race between civilizations. The compass emerged through many acts of observation, touching iron to lodestone, placing it on water, watching it turn, and comparing its direction with the known sky. Human beings in different places shared the same patient capacity to notice. They watched materials closely. They remembered what worked. They repeated useful actions and showed them to others. In a small room beside the harbor, a lamp burns steadily on a wooden table. Outside, voices soften as evening settles over the quay. Footsteps pass along the stone lane. Somewhere beyond the walls, water moves against the hulls of waiting ships. A traveler places a shallow bowl near the light and fills it with water. Another person brings a needle, a sliver of reed, and a dark piece of magnetic stone. The needle is stroked carefully, always in the same direction. It is laid across the reed and lowered until the reed rests upon the surface. A few rings spread outward and fade against the edge of the bowl. For a moment the needle wanders, Then it turns slowly and becomes still. Those gathered around it may speak different languages. One may understand the properties of lodestone, another may know the stars, another may simply remember the method from a distant port. No surviving written record preserves their meeting, yet the demonstration is enough. One pair of hands repeats what another pair has shown. The bowl can be emptied, the reed can be replaced, the needle can be carried onward in a fold of cloth or a small wooden box. Knowledge continues its passage along roads and seas, and as sailors and instrument makers continue to experiment, the delicate needle in its bowl began to acquire a steadier home, a pivot, a marked circle, and a protective case made for the gentle, continual motion of a ship. Chapter 7. The Mariner's Compass. Morning comes quietly to the harbor. Pale mist lies over the water, softening the outlines of warehouses, masts, and tiled roofs. Ropes creak against wooden posts. A sail hangs loose while the tide turns beneath it. Somewhere beyond the harbor wall, the open sea waits beneath a wide gray sky. On a vessel preparing to leave, a navigator checks the familiar signs. He watches the movement of the water beside the quay. He notices the wind against his face and the faint lift of cloth overhead. He knows the shape of the coastline, the location of nearby shoals, and the course that should lead the ship toward its next port. Then he looks down at a small instrument. Inside a wooden box, a magnetized pointer rests upon a pivot. It is free to turn, yet protected from the breeze. After a slight trembling motion, it settles toward a familiar direction. The floating needle in a bowl of water had already shown that magnetism could offer guidance. But aboard a working ship, an open bowl was not always convenient. Water could spill. The floating reed or sliver of wood could drift against the side. A gust of wind, a careless sleeve, or the continual movement of the deck might disturb the reading. Instrument makers therefore found other ways to let a magnetized needle turn. Floating compasses did not vanish at once, nor did every region adopt the same design at the same time. Instead, they were gradually supplemented and in many settings replaced by what came to be called dry compasses. A dry compass does not depend upon a pointer floating in water. Its needle, or another magnetic system, turns around a central point called a pivot. The pivot supports the moving part while allowing it to rotate with as little friction as possible. The idea is simple to picture. Imagine placing a slender strip across the point of a pin. If the strip is balanced carefully, it may turn while the pin remains still. In a compass, the balance must be finer and the pivot smoother. The magnetic needle needs enough freedom to respond to Earth's magnetic field while remaining securely held as the ship moves beneath it. A pivot made the compass more compact. It could be carried in a small container and consulted without preparing a bowl of water. Yet the pointer still needed interpretation. A plain needle could indicate a north-south line, but a mariner usually wanted something more precise. A ship does not simply follow north. It may need to sail east toward an island, southwest along a coastline, or northwest toward a distant harbor. The navigator chooses a course, and the helmsman tries to keep the vessel pointing along it. To make these choices easier to read, makers placed marked circles beneath or around the magnetic pointer. This marked circle became the compass card. A compass card is a circular display showing directions. Early cards could show principal winds or directional points, sometimes accompanied by decorative lines and symbols. Later cards became more detailed. With a marked card, a navigator did not have to judge an unmarked needle alone. A named direction or eventually a numbered bearing could be read from the circle. By the late 13th and early 14th centuries, European mariners were using pivoted compasses associated with marked directional cards. Their construction varied, and the change came gradually. There was no single morning when every floating needle was lifted from its bowl and replaced by one standard instrument. Different makers tried different arrangements, and sailors continued to use the forms that proved practical at sea. In many marine compasses, the magnetized needles were attached beneath the compass card. The magnetic system and the card turned together around the pivot, while the outer box remained aligned with the ship. When the vessel changed direction, the box turned with it. The card, guided by magnetism, continued to show the pattern of directions around the horizon. A fixed mark on the housing represented the direction in which the ship's bow was pointing. By comparing this mark with the card, a mariner could read the vessel's heading. A heading is the direction in which a vessel, or a traveler is pointing. If the bow faces west, the ship has a westerly heading. A bearing is slightly different. It is the direction from an observer toward a landmark, another vessel, or a destination. A lighthouse might lie northeast of the ship, even while the vessel itself is heading north. These distinctions gave navigators a clearer language for movement. They could select a course, observe a bearing, and watch the heading. The compass did not steer the vessel. It did not choose the destination, reveal every hidden current, or replace the judgment of the people aboard. It offered a steady reference, and human attention did the rest. The instrument itself needed care. A bare pivot and needle could be disturbed by wind, spray, dust, and handling. A protective box sheltered the moving parts. A cover might be placed over it when it was not in use, and the housing could be positioned where the navigator or helmsman could see it. In time, a ship's compass was often kept in a special stand or enclosure called a binnacle. The word is connected with an older word meaning a small dwelling. It is a fitting image. The compass had acquired a little house of its own. Within that dwelling, the delicate pivot was shielded from the busy life of the deck. Around it, sailors adjusted lines, raised sails, carried cargo, and moved through rain or spray. The compass remained visible but guarded, a quiet center among many practical tasks. There was still another difficulty. A vessel rarely remains level at sea. It may pitch, moving forward and backward, as the bow rises and falls. It may roll from side to side. These motions can tilt a compass bowl, increase friction around the pivot, and make the card more difficult to read. Even a gentle sea keeps a wooden vessel in nearly constant motion. To reduce this difficulty, compass bowls could be mounted in gimbals. Gimbals are ringed supports that allow an instrument to swing independently of its outer frame. One ring turns along one axis, while another turns along a different axis. As the deck tilts, the suspended compass bowl tends to remain comparatively level. A simple image may help. Imagine a cup carried on a gently moving tray. If the cup is fastened firmly to the tray, every tilt is passed directly to it. But if the cup hangs within movable rings, some of that tilt can be absorbed by the supports. The tray may lean while the cup remains steadier within it. Gimbals do not keep an instrument perfectly level through every kind of movement. A ship can rise, fall, twist, pitch, and roll in complicated combinations. Still, the compass bowl remains steadier through it all. The ringed mounting makes the compass steadier and easier to read than it would be if fixed rigidly to a sloping deck. Now the harbor lies behind the medieval vessel. The shoreline fades into the mist until only a darker band remains. The sail fills beneath a measured wind. The hull moves through low swells, lifting and settling with an unhurried rhythm. Clouds cover the sun. No bright shadow lies across the deck. At night, the same clouds may hide the stars. The mariners continue to observe the sea, the wind, and the behavior of birds. They estimate speed and remember how long they have traveled. They listen for surf near a coast and watch the color of the water. The compass does not replace these skills. It joins them. Near the steering position, the navigator looks into the protected housing. The card shifts slightly as the ship rolls. The pivoted system turns, pauses, and settles. A chosen direction appears beside the fixed mark. The helmsman makes a small correction. Not north, but the course required for this voyage. The distinction matters. North is a reference, one point within a larger circle. From that reference, other directions can be described. The compass gives the mariner a pattern of orientation, while the route comes from charts, memory, experience, and intention. For long stretches of a voyage, the work is quiet and patient. A heading is checked, and then checked again. The wind changes a little. The sea nudges the hull sideways. The steering is adjusted by degrees. No single correction seems large, yet many small corrections help preserve the intended course. The helmsman feels the resistance of the steering gear. The navigator watches the card. Around them, the ship answers the wind and water in its own slow way. It does not move along a perfectly drawn line. Instead, it weaves gently around the chosen direction, returning toward it through repeated acts of observation and adjustment. Under a clear sky, the compass can be compared with familiar celestial signs. Under cloud or fog, it becomes especially valuable because its pointer continues to respond when the horizon has nearly disappeared. It does not need sunlight. It does not wait for a star to emerge between clouds. Still, mariners learned not to treat the compass as an unquestionable voice. A compass could be poorly made, its pivot could wear, and its card could stick. Iron nearby could disturb it. A careful navigator compared one kind of knowledge with another, whenever possible. The direction shown by the instrument was considered alongside the wind, the waves, the remembered coast, and the progress of the vessel. If the signs did not agree, the navigator looked again. The compass was useful not because it removed the need for thought, but because it gave thought another dependable point of reference. In this way, the mariner's compass became part of a wider practice of attention. It was a small instrument, but it did not stand alone. Around it were written sailing directions, remembered coastlines, depths measured by a lead line, the feel of the wind, and a slow account of distance traveled. There were also the ordinary sounds of the vessel. Water moved softly along the planks, timber answered the rise and fall of the sea with low creaks. Footsteps crossed the deck, a loose line tapped gently against a mast. Within the binnacle, nearly hidden among these movements, the compass continued its quiet turning. Its value lay partly in this quietness. The compass offered no sudden command, it simply presented direction again and again. Whenever the navigator returned to it, the card provided a familiar circle, divided into possible courses. The ship might be far from land, yet its heading could still be named. Beyond the vessel, mist gathers in the rigging as fine droplets. The horizon is no longer a clear boundary. Sea and sky meet in shades of gray, and distant features disappear into the soft air. Inside its little dwelling, the compass remains sheltered. The card turns almost imperceptibly over its central point. The ship pitches and rolls, while the gimbaled bowl stays comparatively calm. Each part serves the others. The pivot allows movement, the card makes direction readable, the box offers protection, and the gimbals soften the motion of the deck. A hand rests near the helm, an eye returns to the marked circle. The vessel continues through the mist, not by the compass alone, but with the compass among its trusted guides. Between the unseen sky and the moving sea, the ship keeps its chosen heading. Beneath the card, the magnetized system turns and settles once more, held safely within its sheltered home.